Hi, this is my lab 4 for Physics 2211 at Georgia Tech. This lab is based on oscillations. First, I'll introduce the system and its surroundings. Then I'll go through some key concepts. Next, I'll analyze the motion of the oscillating mass using the tracker software. We'll then create a predicted model based on which we'll create a computational model on GlowScript. Next, I'll compare the results of the experimental and the computational model. And then I'll go through some essential questions. The purpose of this lab experiment is to predict the motion of an oscillating mass using observations from tracker software and creating a computational model that replicates this motion. We'll also be analyzing the different types of energies of the system, such as kinetic energy, gravitational potential energy, and elastic potential energy. The system in this case is the oscillating mass, and the surrounding includes the spring and the earth. However, for energy calculations, the system will include the oscillating mass, the spring, and the earth. So based on the energy principle, the change in energy of the system is equal to the work done on the system by the surroundings plus Q. So delta E is a change in the total energy of the system, W is a work done by the surroundings on the system, and Q is the energy exchange between system and surroundings due to the difference in temperature. This term will be ignored for this lab experiment. Since we are considering the mass, the spring, and the earth to be the system, there is no work done by the surrounding, and hence the total energy is said to be conserved. That means delta K, that is change in kinetic energy, plus delta Ug, which is change in gravitational potential energy, and delta Us, which is change in elastic potential energy, is equal to 0, hence indicating that energy is conserved. So tracker observations, this is for the physically conducted experiment. On the left, as you can see, I've used the tracker software to basically track the motion of the oscillating mass. This gives us the X and Y values of the oscillating mass's position. The X and Y values were then converted into a .csv file format, which will be later used for the GlowScript code. The motion of the oscillating mass began at frame phi. On the right hand side, we can see the calibration which was done to get accurate results. Computation model. The two images on the left highlight the initial conditions of the system. The mass of the ball is said to be 0.402 kilograms. The position and the velocity of the ball are updated using position and velocity update formulas respectively. The X and Y positions of the ball are basically the inputs from our X and Y value inputs from the physically collected data. G is a gravitational constant, which is set to 9.8. The spring constant, which was initially calculated, is 6.83, and the initial length of the relaxed spring is 0.123 meters. The total energy of the system is the sum of the kinetic energy of the ball, the gravitational potential energy of the ball, and the stored elastic potential energy. The formulas for this were shown in the previous slides. The net force acting on the ball is the resulting sum of the spring force and the gravitational force. This is then accounted in the velocity update formula to map the motion of the oscillating mass. The change in total energy of the system is the final energy minus the initial energy, which is basically the final sum of kinetic, gravitational potential, and elastic potential energies minus the initial sum. The results of the two models, overall, the computational model does a really good job in predicting the motion of the oscillating mass. However, as we can see, the experimental data collected, the peaks of the red curve do not really overlap with the blue ones, and so there are troughs. This is because there's a damping effect due to the air resistance, which we have not considered, due to which there is some loss of energy from the system to the surrounding. Therefore, the external forces of air resistance, drag, account for the possible sources of errors for this experiment. Therefore, by considering a drag factor, we can improve the accuracy of this lab experiment. Moving on to the discussion questions. Is the total energy of the system conserved? Yes, it is conserved, as we are considering the mass, the spring, and the earth all to be a part of the system. Hence, delta E will always remain 0. This is indicated by the orange horizontal line. Delta E is equal to 0 at all times. Average oscillations in the X and Y directions. The time period for an average oscillation in the Y direction is slightly less compared to the average oscillation time period in the X direction. This is because the force of gravity has a greater impact in the Y direction, resulting in a lower average oscillation time.